it'd be 409.98.
Yeah.
Just like that. That is a 4. Oh, units? All right, so let's see what it would sound like, and then we will compare it to that. 409.98. Now, they won't sound exact, one, because it's a physics demo, but two, the timbre is different. The material causes some differences also, but this should be the second harmonic. Now, if we do it at the same time, we might be able to get beats going. In other words, there could be an extra trill in there. I hear the trill. I don't know if you can. Could you hear the trill? Okay, at least two of you could. Couldn't think so. You didn't hear that? No. Well, let me talk to you two then. I'm gonna do it one more time, just listen for it. If I turn this down, like down a little bit.
That can make you hear better. Yeah.
Yeah, but it's not perfect. All right, let's make the next prediction. True to form, I put it over there. All right, so how many waves will the next harmonic be?
1.5.
Yep. So I got one full wave right there, then plus 2/4. So I got 1.5 waves would be the length. And so the wavelength would be 2/3 of L, so 2/3 of 0.84 meters. So what is the wavelength?
.56 meters.
0.56 meters. Based upon the speed of the wave, assuming the temperature hasn't changed at all, we end up with frequency is equal to speed divided by the wavelength. So 344.38 divided by 0.56.
I got 614.96.
14. Okay. Yeah. .97. Yeah, that's it. You Again, I'm hearing a little extra trill in there.
The trill was a lot more that time.
Okay. You couldn't hear it that time?
No. I easily heard it the first time, I could not hear it.
Is that like a biological thing? Like people just hear different frequencies better?
Well, people do hear certain frequencies better, but, I don't know if this can be explained by that. Let me turn that down some. Is that hearing it at all?
I mean, I hear it like coming in and out, like I hear like the volume kind of going up and down, but like I don't hear like a trill the way I heard it the first time.
I agree.
Like the first time I told Coy, it sounded like the second harmonic, it sounded like a cat purring. I easily heard that.
Okay.
I couldn't hear that at all in this one.
Did you hear both?
I heard both trills. The first time I did this harmonic, I heard it better than I just did. But I think this is how people can tell the difference between us. Is they'll just play that and see what people hear, and then they'll be able to identify us. All right, why don't we take a small little break here, and I'll set up for the two fixed ends, and then we will hopefully show that physics makes some sense, or at least provide evidence for that. Hit pause. Yes? All right, so so first let's talk about finding speed of a wave through something other than air. As a general rule, the speed of a wave depends upon two factors here. There is a force term and an inertial term. Now there's a video that I present which goes through derivation of this. I know we've got several calculus ones. I think I have a non-calculus version. So remember that for a wave to propagate, it's when one particle moves, how does it affect the next particle? Either whether it runs into it or whether it's pulling and drags the next one with it. The inertial term is basically how much mass am I trying to move? The more mass, the harder it is to get things to change. And so specifically for one-dimensional, so something which is very skinny compared to the other two, a length, this would be the square root of the tension over the linear density. So what's the formula for linear density?
Mass over volume.
That would be for density. All right, so the formula for density, mass over volume. Then there's surface density.
Surface mass over surface.
It'd be mass over,
Surface volume.
what's
surface
surface
area?
volume?
Surface area.
There we go. That's mass over area. And then linear density,
Is it tension times V
no,
squared?
just in the same vein as what we have over there.
It's mass over the length.
Yeah, mass over volume. So I have this string here. This is what we're going to use to actually do the vibrating part. But I have another piece of string here that we just need to find the mass of it and the length of it, and the world becomes a better place. set there. We'll All right, so the length of this piece of string is 135.55 centimeters. So 135.55 centimeters or 1.355 meters. Having done enough of these experiments and seen students do enough of these experiments, this is generally where the biggest problems come in, which is one of the reasons why I wanted to make sure it was zeroed before I started. That if the balance is off by 0.2 grams to start with, and you find the measurement of this as 0.6 grams, well, you've already introduced a 33% error into the problem. So I made sure it was 0. The mass really should not be a whole lot here. Pretty close. Just slightly off. Looking little to me, and so I've got a mass of 1.41 grams. So 0.00141 kilograms. And so what do we get as the linear density?
.00104.
0.00104.
Yeah.
Units?
Kilogram per meter.
Yep, absolutely. Now, I don't know what the tension is, but I can come up with a pretty good idea of it. Wrong way. Now, as I do this, I'm going to be applying mass to this string so that I can get some idea, so I can sort of set the tension. But as I do it, depending upon how much mass I put on there, it's possible that these things will start to move, and so I need to clamp them down. And so somewhere on this table, there they are some clamps. Now, in terms of the lab version of it, you run into an issue with the longer the string is, the easier it is to find the higher harmonics, but it requires a whole lot of mass to get the lower harmonics. So there's the potential issue of the string breaking, or the pulley breaking. But the trade-off is that if I go for a shorter length, then I don't have to apply as much mass, less chance for the string to break. But getting the higher harmonics is more difficult. So about a meter is decent enough. I did, in the video that I did for this, I think I went 2 meters long, but ended up, the string broke more than once. All right, my pulley. I'll grab two of them. The fine motor skills required. There it is. Come through. There we go. Now, I don't want whatever I'm hanging on this to be touching here, because that introduces another force. So I'm just gonna put forgot the name of this type of knot. A non-functioning one. I did start the recording again, didn't I? Can't tell.
I can't tell.
On there. Any vote now. There we go, finally.
Yep.
The red dot is blinking. Now, without putting any mass on it to start with, if I turn it on, we can start to see some of the harmonics here. Lined up better. Oh, okay. All right, so as I apply more tension here. So we've got the first harmonic, less tension. Got multiple harmonics. Was that it? Second harmonic. I assume that you can see it. Somewhere around there is the second harmonic, a little less tension. Third harmonic, and then keep going. So we're now going to apply some mass. This is roughly 500 grams. That level.
Higher. 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 That's good. A little higher. That's good.
All right, so depending on which harmonic I want to get, let's go for the first harmonic, so I need to add more. Add another 200. Actually, I got 2 sets here. Let's add another 500. See what that does. So I know I probably need to add a little bit more. Part of it is I've got a note over here, and I don't know if you can see it, but just imagine on the pulley, at the top of the pulley, it's not vibrating much. And the other note is here, it's not over there quite yet. And so I need to add more in order to move that node that way. See a little bit more. That's really close. A little bit more, what does that do? That suppresses it a little bit less. So something less than that. And for the sake of this, we're just gonna call that one close enough for right now. All right, so I know that at least here, the tension in this string right here should be equal to the weight of what's hanging off of it. If we assume that the string is massless, that's legitimate. If it's an ideal string, then that would be the tension throughout the whole bit. So let's figure out how much mass this is. And I'm going to trust the manufacturer for the sake of this. However, in a lab, you don't necessarily want to trust the manufacturer. So I got 500, 250. So, right, this is the one I took off. So the hanging mass was 1,250 grams, 1.250 kilograms. Winston-Salem, 9.798 meters per second squared. What is the weight? What is the tension? What was the tension in the string?